Hi, this is going to be our last lesson on states of matter. This is going to be talking about gas behavior today. Okay, so gas behavior, our essential question has been, what causes matter to change from one state to another? These pictures should jog your memory. On the top left, we have states of matter. We talked about those. We talked about how heat transfers. We talked about gases a little bit, and now we're going to get to the final part here, the different gas laws. So let's continue. These are our science standards, which stay the same throughout the year, that are on your report card. These are our substandards. This is the substandard we've been working on. Develop a model that predicts and describes changes in particle motion, temperature, and state of a pure substance when thermal energy is added or removed. Okay, our objectives are here, which we will go over at the end. Your questions today are these objectives, and we are also making them a summative assessment for the video today. So they will count as a test grade. So these are some of the objectives. These are the rest of the objectives, which we will get to at the end. Okay, how does a snow globe resemble a gas? Well, if you think about it, the faster that you shake a snow globe, the faster the snowflake particles move around and they collide with each other, and they collide more with the walls of the snow globe. So if you stop shaking it, then the particles settle down and they don't move as fast. So the slower you shake a snow globe, the slower the snowflake particles move around, and the less they collide with each other and the walls of the snow globe. This resembles a gas. So what is pressure? So the gas particles are doing what the snow globe does. They are constantly colliding with each other and the walls inside of their container. So this pushing against the walls of the container is called pressure. So it's a pushing against from the inside. That's what pressure is. So the pressure of a gas is the force of its outward push in newtons over an area in square meters of the walls of the container. So think of it as pushing outward, pushing from the inside out, okay? That's what pressure is. So how is pressure measured? Well, pressure is measured in units called pascals. So this guy, Blaise Pascal, was a famous mathematician and a scientist, and he studied gas pressure. So it is very fitting that pressure is measured in units called by his name. So we measure it in pascals. So 1 Pascal, it's abbreviated PA, is equal to 1 Newton of force applied over an area of 1 meter squared. And that is the SI unit. Pounds per square inch is the United States unit. There are larger units also that are called kilopascals, and there's a little K in front of them. So 1 kilopascal is equal to 1,000 pascals. So sometimes you'll have that measurement. Okay, how does pressure of a gas affect the physical properties of an object? Let's take a look at a volleyball. So a volleyball feels firm when the pressure of the air inside of the ball is greater than the pressure of the air outside of the ball. So the pressure again comes from the inside pushing outward. So that's the way the pressure goes, those arrows on the bottom right. Gas pressure goes out. So gas particles inside the ball are closer together than gas particles outside of the ball, which makes sense. There's less space inside the ball than there is outside of the ball, which then has the entire pretty much universe, correct? So more frequent gas particle collisions occur inside the ball, resulting in higher pressure inside the ball. So smaller space, more collisions, they push out towards the edges of the ball, making it firm and ready to use for volleyball. However, what happens if you get a hole in the volleyball? Well, the air will leak to the outside of the ball because the pressure is greater on the inside of the ball, forcing the air out. So if you think about it, you have more pressure inside the ball, the hole happens, the pressure of the gas wants to squirt out of the ball. So the pressure inside the ball drops until it is equal to the pressure outside the ball. So then everything equals out, and then you get a flat volleyball. Okay, what happens when you heat a pot of water on the stove? Well, it boils and bubbles start to appear. The hotter the water becomes, the faster the bubbles move and collide together. This is very similar to boiling gas and how it reacts. So gas is like the boiling water when it heats up. The hotter the gas becomes, the more the gas particles move around and collide with each other in the walls of their container with greater and greater force. A greater force over the same area means greater pressure. Okay, more force, more pressure. And this is example here of some molecules of gas in a cold environment versus a hot environment. They spread out, or try to, but if they're enclosed in a container, they start putting pressure on the walls of the container. How does temperature affect pressure? Well, these are important to know now. You're going to have to get all of these straight and figure these out and remember these and memorize these. When the temperature of a gas at a constant volume increases, the pressure of the gas increases. So this is, the volume is kept constant. So the container is not made bigger. The container is not made smaller. The container stays the same. So you heat up the gas, the molecules are going to collide together more, and it's going to create more pressure from inside the container as the molecules push against the walls of the container. So as temperature increases, pressure also increases. And the opposite is also true. When the temperature of a gas, again, the volume is kept constant, you're not changing the size of the container, the temperature decreases, the pressure of the gas will also decrease because the molecules won't be moving around as fast. They're not going to put as much pressure on the walls of the container. So as temperature decreases, pressure also decreases. So note, these rules only work at the same volume. If you start changing more than one thing at a time, these rules are not going to apply the same way. Okay, does temperature affect density? Let's think that one through a little bit. So most substances become less dense as temperature increases. So that means the molecules are spreading out more, which makes sense because as you heat things, they get more energized and they try to spread apart. So as temperature increases, density increases. Decreases, I'm sorry. Okay, so most substances become more dense as temperature decreases. Okay, so as temperature goes down, density increases. So this is an inverse relationship. Okay, indirect relationship is another way of saying it. Temperature makes atoms expand. Okay, let's keep going. Who was Jacques Charles and what was his law? Okay, there's a picture of Jacques Charles. He was a Frenchman, a French scientist, and he discovered a relationship between temperature and volume. He did this back in 1878. Volume of a gas, I should say. So let's see. The relationship he discovered was called Charles' law, and we still use his principles today in many ways. Here are some examples of ways that we use Charles' law in everyday life. A hot air balloon, baked products, helium balloons on a cold day, pop-up turkey timer, opening a soda can, bursting of a deodorant bottle. Charles' law, how does temperature affect volume? So here's his law. Now you got to know this. So when the temperature of a gas at a constant pressure increases, the volume of the gas increases. So now we're keeping pressure constant, but we're increasing the temperature. Then we're allowing the volume of the gas to increase. And that makes sense because the molecules under heat get more energized and want to expand. Okay, so as temperature increases, the volume also increases. The opposite is also true. When the temperature of a gas at a constant pressure decreases, the volume of the gas decreases, which makes sense. Less energy, molecules don't move around as much. They get closer together, they get more dense, the volume will decrease. So temperature decreases and volume decreases as well. So that is Charles' law. Note that these rules only apply at the same pressure. You start moving things around, besides pressure being held constant, and you got different changes happening. Charles' law, how does temperature affect volume? So I'm going to put this video on, and we're going to watch a cool experiment. So as temperature increases, remember, volume also increases, right? And as temperature decreases, volume decreases. So this is putting a balloon into very, very cold liquid nitrogen. So let's play that. See if I can get it to play here for you.
What's up, everybody? Welcome back to my laboratory where safety is number one priority. And today we're going to put balloons into the liquid nitrogen and let's see what happens. Okay, once again, I got here liquid nitrogen and we'll pour it in a bowl. Whole bunch of it. Look at that, so cool. Just a little bit more, and that's it. Put that away. Okay, and now I'm just gonna put these balloons inside of it. Let's see what happens. Actually, I need something to push it in. Wow, look what happens to those balloons. That's so cool. Wow, this is so awesome. Too much fun. Wow, it turns out like a paper. They don't even pop, they kind of deflate. Oh, sink it all the way in. Wow, this is so awesome. Couple more. Yep. We definitely need to help it for it to deflate faster and sink it in. Let's try a bigger one. Well, I used a little bit too much of a liquid nitrogen. Maybe I'll just pour it back when I'm done. Wow, look at this. This whole big balloon is shrinking as well. Here you go. Oh, it got stuck. No, don't get stuck. Here you go. Whoa, this is insane. Do you hear it crumble up? So crazy. Okay, now what I'm gonna do is put it aside. And guess what? I'm just gonna pull them out and put them right here and let's see what happens. Look at them. This is like Terminator 2. Remember that when he put back together the liquid one? Whoa, look at that. This is so awesome. Woo! One of them popped. That was kind of scary. Look, I can even hold it. And because I'm holding it, it's actually... Ah! That's so scary when they pop. That's kind of awesome. Well, some of them have popped. There's a big one. Let's see what happens. Will it pop or will it survive? This is so cool. What do you guys think? Go back to normal. No big deal. This is so awesome. Definitely a really cool experiment with liquid nitrogen. And look, it's back to normal. One more time. Look at it shrinking. So cool. It feels like just plastic. It doesn't feel like a balloon anymore. I'm gonna pull it out and put it in my hand. Lift it up. See what happens. Look at it. My hands are warm. I made it up even faster. Wow, look at that side. So my hands are warm, so that's why it's coming back a lot faster. And there you go. regular balloon. Awesome. Well, guys, if you like this video, please give this video a thumbs up. It helps.
Okay. So remember, as you increase the temperature, the volume increases. As you decrease the temperature is what he did. Then you decrease the volume. That was really cool. All right, let's continue. A directly proportional relationship, temperature and volume. So the graph of Charles' law shows that the volume of a gas is directly proportional to its Kelvin temperature at a constant pressure. Kelvin temperature is used because it is absolute zero. It is like the complete absence of any heat energy. Achieving absolute zero is almost impossible because everything has a little bit of heat of some sort. However, kelvins are used for that reason. But if you wanted to convert it back to Celsius, you would add 273 to any temperature of Kelvin that you have. So let's take a look at the graph. Notice how it's a linear relationship, and we have temperature on the bottom here, and we have volume going up the side. So as temperature increases, volume also increases. This is an increasing slope. And we also notice that there is a constant slope because it is a line. So as the independent variable temperature increases, the dependent variable volume will increase at the same rate. There is a constant slope because it is a linear equation. And as the independent variable temperature decreases, the dependent variable volume decreases at the same rate. It is a constant slope. So it is directly proportional, temperature and volume. Okay, so if we have 0.500, 200, what does that mean? Well, that means at 500 degrees Kelvin, the gas volume will be 200 milliliters. If we were to increase the temperature, the gas volume would be going down. Would be going up. So notice an increasing slope equals directly proportional relationship. Okay, who was Robert Boyle and what was his law? So here's Robert Boyle. Robert Boyle was an Irish intellectual who discovered a relationship between gas volume and pressure. So now you have to know the difference between these two laws. So the relationship he discovered was called Boyle's law, and we use his principles today in many ways. Here are some examples: in spray paint, human breathing, working of a syringe, scuba diving, a bicycle pump, and the storage of gas. Okay. Boyle's law, how does pressure affect volume? Well, let's think about this. When the pressure of a gas at a constant temperature increases, the volume of the gas decreases. So as pressure is increased, volume is decreased. Or you could say as volume is decreased, pressure is increased. When the pressure of a gas at a constant temperature decreases, the volume of the gas increases. Also notice that the temperature is held constant. So as pressure decreases, volume will be increased, or as volume increases, pressure will decrease. These same rules only apply to the same temperature. Okay, let's remember our Boyle's law. Pressure increases, volume decreases. Pressure decreases, volume increases. And I have a video demonstrating these.
In a demonstration of Boyle's law, we'll place a balloon in a vacuum bell jar. We'll apply a vacuum, which basically pumps out the air in the bell jar. The pressure outside the balloon will be greater than the pressure inside. The balloon expands to try and equalize the pressure. Volume and pressure are inversely related to each other. When we release the vacuum, the pressure increases and the volume decreases. As another demonstration of Boyle's law, we will put a marshmallow peep into our vacuum jar. The marshmallow contains air trapped in a mixture of gelatin and sugar. As we apply the vacuum, the pressure outside is lower than the pressure inside. The air in the peep will expand to try and equalize the pressure. When we release the vacuum, the pressure increases and the volume decreases. As another illustration of Boyle's law, we will put some shaving cream into our vacuum jar. The shaving cream contains air trapped in a soap mixture. As we apply a vacuum, the pressure outside is lower than the pressure inside. The shaving cream will expand to try and equalize the pressure. As you decrease the pressure, the volume increases.
Okay, there's some examples for you. So as pressure is increased, the volume is decreased. As pressure is decreased, the volume is increased. I want to play that again. All right. Boyle's law. How does temperature affect volume? Same thing. A bicycle pump will show us Boyle's law in action. So here's a bicycle pump. This is the part that you push, right? So when you push down on the pump, right, you're going to push this way, the volume inside the bike pump decreases. So it started out with, let me get my little spotlight here. It started out with this whole area with volume, right? But there's this little bar that's not allowing it to have as much volume. So as you push down on that, the volume is only this much now, right? So as the volume decreases, the pressure of the air will increase, right? It's getting squished together. It wants to come out. It's forcing itself against the walls of the container. And so it pushes out by this little tube here and into your tire, which then inflates your tire. So let's see how that looks. So we push down on the handle. Volume inside the pump is going to decrease, and the pressure is going to increase and squirt out into the tire to pump it up. So that's an excellent example of Boyle's law. Okay, it should say an inversely proportional relationship, pressure and volume. So the graph of Boyle's law shows that the volume of a gas is inversely proportional to its pressure at constant temperature. Remember the constant temperature. So notice how the slope is downward, but notice also that it's not a straight line. It's not a linear relationship. It is a function, but it's not linear, which means that the slope, the rate of change, is happening at different numbers. So as the independent variable, the volume increases, the dependent variable, the pressure decreases, but not at a constant rate. And as the independent variable volume decreases, the dependent variable pressure will increase, but not at a constant rate. The slope is changing. So we have 0.3441. What does that mean? Well, that means at a gas volume of 34 milliliters, the gas pressure is 41 kilopascals. Notice how a decreasing slope is present. This shows an inverse proportional relationship. One increases, the other decreases. Okay, Boyle's law in action. Pistons are a type of gas pressure cylinder that are often used in machines such as cars. A piston is an example of sort of like the bike pump that we just saw, and how there's a thing in there that can increase and decrease the volume inside of the cylinder. So pistons move in response to the motion of the particles of gas. The moving pistons help to turn the crankshaft, which connects to the wheels of the car. So the pistons drive the turning car wheels. So let's see an example of that and how that works.
Piston moves on its first downward stroke. The intake valve opens to allow a mixture of air and fuel to fill the combustion chamber. This is called the intake stroke. Next, the intake valve closes and the piston moves on an upward stroke that compresses the air-fuel mixture. The compression of the air-fuel mixture will make it combust with greater force than if it were uncompressed. This is called the compression stroke.
So less volume now, you notice how this is moving up. Less volume is going to put greater pressure, and there's also some gas mixed in here, so it's going to ignite this little doohickey here up at the top. We'll see that in a minute.
Third, the spark plug ignites the air-fuel mixture, causing it to burn explosively, which forces the piston into another downward stroke. This is called the power stroke. The fourth stroke is the exhaust stroke. As the piston begins its second upward stroke, the exhaust valve opens and the burned air-fuel mixture is forced out of the combustion chamber.
So notice how it's forced out now because all the pressure is building up as the volume is decreasing.
Through the exhaust valves. Two terms you may be asked to explain to customers are the engine's compression ratio and displacement. Compression ratio is the ratio between the total volume of a combustion chamber and cylinder when the piston is at the bottom of its stroke and when the piston is at the top of its stroke. In this example, the compression ratio is 10 to 1.
Okay, that's how a piston works and how Boyle's law applies to it.
Piston moves on its first downward
I'm
stroke.
trying to pause
The
that.
intake
Okay. All right, here are your questions. And your questions are on a Google form this time, so you can just type your answers in. So number 1, define pressure. Look on the slides. I'm sharing the slides with you, please. List the units of measure for pressure over a given area. Explain how gas pressure affects the physical properties of a volleyball. Explain how temperature affects pressure and why. Explain how temperature affects density. Explain Charle's law in relation to temperature and volume. Explain if temperature and volume are directly or inversely proportional and why. List 2 real-world uses of Charle's law today. Explain Boyle's law in relation to pressure and volume. Explain if pressure and volume are directly or inversely proportional and why. List 2 real-world uses of Boyle's law today and explain how a piston uses Boyle's law. I'm going to count these questions as a test grade, so please do your best. And that's the end, so I'll see you next time. Bye.